So something is CPU intensive in our application, and we have found out that the get URLs endpoint is CPU bound and it's blocking the event loop. And what can we do about it? So one thing that we can do is to split computationally heavy parts with apart from the I/O heavy parts, and put the computational logic in a separate service or a separate container of its own, and keep the I/O logic on a separate server on its own. So why am I putting those two into different servers and not leaving them on the same box alone? There are a bunch of reasons for that. First of all, if you are using a infrastructure as a service solution like Rackspace or AWS, then you are familiar with the fact that there are different sets of virtual machines optimized for different kinds of users. So it makes more sense to put a CPU-bound application to a virtual machine that is optimized for CPU loads, and an IO-bound part of your application, like the routing layer, to an IO-optimized virtual machine. But even if we do that, we'll still have to increase the performance of our application because it's still really slow. And to do that, there are a bunch of things that you can do. You can either write your CPU-heavy logic in a compiled language like C or C++, and then use child process to fork your application and get the results. And this, in general, it depends on use case, but I have seen that this kind of an approach is 10 to 100 times faster than writing plain JavaScript. And you may also come up with a native Node.js module, which is more or less the same thing. You write C++ code that does the same logic. However, you won't be dealing with the burden of forking a child process, so you'll be closer to the libuvi's thread pool, basically. So it gives you much more power, but your code will be much more uglier too. So I would dive into this alley or the other one unless I have to, but sometimes you have to and you don't have any option. So these are options to optimize a really CPU-intensive, CPU-bound application. And the other thing might be to put it on a beefier server so that it performs faster. But in the end of the day, you'll eventually have to optimize it. But no matter what you do, as we said, you'll have to refactor your compute logic and put it onto a separate service first. And to come with that kind of a scenario, we'll split our application into two parts. One of them will be our API service, and the other will be our compute service. And we'll be binding them or joining them loosely with a message bus in between. And there are a lot of message bus implementations or implications that you can pick from. This queues.io is a web page that lists them all and compares and contrasts them. And in our samples, we are using RabbitMQ, but it doesn't matter too much. And the message bus topologies are more or less similar in whichever architecture that you use. And I won't dive into details of message bus topologies, but we'll use the worker queue approach in our application. So how it works is, currently we have a single API service and a single compute service. However, we are envisioning a place where we can have more than one API services and more than one compute services, and it doesn't matter where those API and compute services live. It can be in the same box, it can be in different machines and stuff like that. We'll be sending a request to the request queue of our compute cluster, and that request will be dispatched in a round-robin fashion to a compute service, and we do some computation, and we put the results back to the response queue of our API service. And then API service takes it and displays it to the client, basically. So this kind of a segregation enables us to do a lot of things. First of all, we can scale our compute nodes, API nodes, and even the message queue separately and independently from each other, which is really useful because your compute services and your API services scalability needs are different. They might have different scalability requirements. And also, the scalability characteristics of your API service might change differently over time than your compute service. So this loosely coupled flexibility gives you a lot of options to adaptively architect your application, basically. And also, it makes sense to cache all the things, I can say. So you can utilize a caching mode. You can put an in-memory cache in your API service so that you don't have to make this computationally expensive requests over and over again. And similarly, you can even put a cache layer on your compute service too. And using the cache is not rocket science. You just simply get the response out of your cache object, and if it's in the cache, you kind of return the outcome of the cache. And if it's not in the cache, you make a request to your queue or your message bus and wait for the result to come backwards, and then cache it basically. So this is how cache works. But since we are starting to split our application and separating our concerns, it will become a little fragile. And it will become more likely that one or more of your application nodes might crash. And actually, it's not a matter of if. So it's not if your application node will crash, because processes will die. So it's not a matter of if, it's a matter of when, and it's a matter of how frequent. And this simple script is actually pretty good enough. So when a process crashes, you can restart your process, and you can resume your life from where it left out. But there are other process managers that you can utilize too. And I use Forever because of its ease of use. But any of the tools that is listed here will be adequate. And there are a bunch of tools that are not listed in this slide as well. So just pick one and use it. But you should be aware that you will need to manage your processes somehow. And using Forever is relatively easy. You call Forever, and then you pass it a bunch of options, like you can put an output path so that you can put your log files to a certain directory, and then you can configure a log rotation script to rotate your logs so that it doesn't populate your entire disk and you run out of disk space basically. And this abort, --abort on uncaught exception is not a Forever specific argument, it's Node.js specific. When you provide this flag, whenever the Node.js service, your Node.js application crashes, it will take a core dump for you. And the core file that this flag creates is really important because it gives a canonical representation of your entire system at that point, so that you can use something like a MDB and then drill down into what's the cause of the crash. You can look into stack traces, stack frames, and see the exception. Maybe you can, for instance, maybe you get a null pointer exception from your code, or maybe a library that you're using is causing the crash, or maybe the problem is even in the Node.js core itself. And without taking a core dump and doing this kind of a post-mortem analysis, it's really virtually impossible to figure out what's the root cause of the problem by simply looking at your logs, for instance. Yep.
What was the debugger you were using for the core dump?
It's called MDB, and it runs on Solaris systems. So the way that we do is, and I don't know whether it's the ideal way, but we have a Solaris testing box. So we take the core dump, put it onto a Solaris, and debug it basically. It's kind of MDB, M as in mountain, D as in DB as in database. So that's that thing, which segues us to the lovely topic of debugging. So debugging is not the favorite thing that everybody wants to do, but you'll have to do it anyway. However, I'd like to, before starting the topic of debugging, I'd like to debunk a bunch of myths related to Node.js and debugging. First and foremost, debugging in Node.js is not hard nowadays. And also debugging in Node.js, some people claim that it's still immature, but it's not the case, at least right now. You'll have to be able to debug Node.js, you'll have to know your tools and use them wisely. And when you do that, it's really relatively easy to debug and profile your Node.js applications. And when it comes to debugging, there are two types of debugging. One of them is live debugging, and the other is post-mortem debugging. And I'm also putting this remote debugging into the live debugging bag because you are remotely debugging a live system, basically. So live debugging is like there is a tornado wreaking havoc in a city, and you are observing it, and you are trying to locate the butterfly that created this tornado initially. Everything is changing all the time. So it's kind of like being a physician and you're analyzing the vitals of a patient, And the patient might die, the patient might get better, but you'll have to use your intuition to come up with the root cause of something. So it's it's dynamic. There is a lot of dynamism in remote live debugging, basically. And on the other hand, postmortem debugging is like making an autopsy. The patient is already dead, basically, and you are just bisecting to find out what has happened for the crash of the system. It's more or less like being a chemist in a lab. You have a lot of data points from your lab experiments, which I hated them, by the way, but anyways. And then you kind of form a hypothesis around your data, and you try to either support your hypothesis or refute your hypothesis by collecting additional data. And when you rinse and repeat this process over and over again, you can come up with a holistic understanding of the root cause of your system. So it is more scientific, and it's relatively easier to figure out the root cause of a problem by analyzing a core dump in a post-mortem fashion than directly tapping into a service using a REPL and trying to find out what the storm is about, basically. And related to debugging is profiling, and there are two kinds of profilers that you can use. You can use kernel level tools, and as I said, dtrace is one of those. And if you are using Linux, perf events is one of the other tools that you can do dynamic tracing. And in Windows, there is the xperf, which is, I don't know, perf for X Windows, I think. And I haven't honestly done it in a Windows environment, so I cannot comment on that too much. So since they are kernel level, they can be used in production because they have really low overhead. And you can also use V8 profiler. However, the V8 profiler is not suitable for production because it brings a lot of overhead to the performance of your application. Yet the V8 profiler is really useful, at least for debugging purposes or development purposes. So both of these tools have their own uses and their own applications that we can use. And using the V8 profiler in source code is relatively easy. First, you import this V8 profiler module, and then you call start profiling, and then you'll call this stop profiling method after a while, and it will create a bunch of output for you, which you can stream it to a file, CPU profile file, and then you can use some tooling to analyze it. And we'll see some of them with a demo. So I'm checking my time. We have still a bunch of time. Let's go back to, oops. Okay, so I'll exit here. So I'll do a Docker PS. I have, let's do something else. So I have Bastion, demo, and web instances. So I'll Docker stop, Fluent, Bastion, Fluent, web, Fluent, demo, enter. Do a Docker PS again. Okay, so my setup is clear, and then I'll start this 008 cluster setup, basically, which will create a simulation of this message queue along with this compute service and the API service, as it has been depicted in the slides, a couple of slides before. So to profile it, I'll go to my Fluent Bastion host. So let's do Fluent Bastion. And I'm going to use the Vantage again. So to use Vantage, I'll do Vantage. Let's go actually to something that is, all my files are messed up. So yeah, this is better. So I have two folders. One of them is the data folder that is shared by the Docker hosts, and the other is a working directory of my application. So I just want to show you what kind of files are created when I call some certain Vantage commands, basically. So for that, I'll do, come on. Docker, I'll go to this Bastion host again. Fluent Bastion. What? No, not Docker Bastion. Okay. Live coding. I love it. Fluent Bastion. And then I'll do Vantage to my app instance on port 8004. And I'll do help. So I can do a bunch of things. When I call dump, it will take a core dump for me. If I do a snapshot, it will take a heap snapshot. And I can also toggle profiling on and off. So I'll start with this dump thing. When I do this, as you see, it creates this core file, which then we can take and analyze with MDB. And if I do a snapshot, and you don't have to remotely connect to your service to do this. You can schedule a script and do whenever there is some kind of a CPU issue, you can take a core file, or before the service crashes, just take this snapshot and dump and stuff like that. So if I do a snapshot, for instance, it takes this heap snapshot file, and let's do this profiling as well. I'll toggle profiling, and I'll toggle profiling again. And it creates this CPU profile file. So there are a bunch of tools to analyze this. Since I am a little lagging behind time, I'll just show a bunch of them quickly, and I'll skip to the next part of the slides. But before that, I'll just want to, where am I? I'll just exit here first. Exit. ls. Exit. Come on, I want to go out. Exit. Yes, I want to kill you. Okay, so I will run this node get tags loop again so that I can do some cool stuff, hopefully. Let's go. Yeah, this is my Bastion host. I'll also exit it, and then let's see what kind of machines that I have. I have this Fluent. Okay, I have this Fluent app, so I'll just go into this app node. Fluent app. I'll go to my working directory, and this service is using forever, so I can do a forever list, and it shows what kind of service is running on my machine. So to stop this, I'm going to do forever stop 0, the number of the stop, and if I do again a forever list, it will say that no process is running. The reason I did this is because I'm going to run this node process with certain flags. So if you run this node with this profile flag and you provide a bunch of different options, then it will take a while, so I'll just cancel it, but it will create for you this isolate blah 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 log files. Then you can take this isolate log and analyze it in a different tool. And to see what kind of flags that your Node.js runtime provides you, you can do node -v8 options. And there is a huge list of configuration stuff that probably a minority of you is aware of. And these are really useful to debug stuff in production. But I pray for you if you have to do this, basically. So that creates this isolate log. And you can do something like, not this one, like this as well. You can expose the garbage collector to your system and trace what the garbage collector is doing. This is also really useful, especially in development. It shows you when this garbage collector is doing a mark and sweep garbage collector, what your heap utilization is, what's happening in the background memory-wise. And again, if you have to do this, I feel for you, but there's the option to do it. So the final thing that I'll show you is I'll run this node project in debug mode with --debug flag. And when I do this, it will start the server on a debug port. And I can attach to this remotely. This is my web storm on my local machine. It's not even on a Docker host, obviously. And I can simply provide an IP address and a port to start a debugging session. So when I run this, it will load the debugger. I can see all my scripts, and if I set a breakpoint, it will stay at that breakpoint, and I can do all the regular things like stepping in, stepping out, stepping over, and stuff like that. And I see all the environment variables like my key, my parameter, and stuff like that. So it enables you can debug Node.js in runtime remotely if you run it with a -- debug flag. And we have created a bunch of profile files. So I have loaded them before onto WebStorm to save some time. And to load them, if you are using WebStorm, of course, other IDEs or other tools have different ways of doing it. But if you are using WebStorm, you can go to this tools, V8 profiling, and then do analyze V8 profile log to analyze the log. And you can do analyze heap snapshot to analyze a heap snapshot. And the profile log gives you, first of all, it gives you a wonderful flame chart so that you can see what's happening in your application at any given time. And you can right-click and go to the source code and correlate the time it takes for that thing, and the source code is it's accompanied with too. And this pink thing, I don't know if you can see this, but this pink thing is the garbage collector being triggered. So you can also visualize how long it takes for the garbage collector to execute and how long your application is stopping when it does a garbage collection. So additionally, there is this bottom-up view, which stacks all your functions in the order of the most performance it consumes or the most time it takes on the CPU. So it looks like the GraphQL library's getVisitor function is taking around 18% of the CPU time. So it might be a place that I might start optimizing. It might or might not be. So I need additional data to dive into it. So that's it for the V8 profiling. And for the heap snapshot, I also have loaded it. It's not different from doing a heap snapshot analysis in Google Chrome. So I'll just quickly go to something that I know. So this is the global Fluent object that I have created in my source code. And I have this resolvers connection in the Fluent object. And the good thing is, I don't know if you have done heap snapshot analysis, and if you have done it, I again feel for you. But the good thing about this tool is I can mark this ID, like I can say resolvers, for instance. And it kind of creates this red thingy next to it. And it's really easier to mark this thing instead of noting down object IDs and trying to figure out which object ID is correlated to which other thing, basically. So I can, for instance, I can go to a different containment view, and I can easily see that my marked instance is down here and it's corresponding to the same object. So that's all there is for the heap snapshot analysis. And I'll see another visualization. This is a browser-based thing. You can go to this address. If you Google profviz.html, probably you'll find it. So it's this kind of a tool. You load this V8 log onto it, and it will give a graphical representation. It's not as pretty as the WebStorm one, but it gives different visualizations for you. For instance, these green things are optimized code, and the red things are not optimized. So I can see that in the middle of this flow, I am running mostly optimized code, and to the end of this application, it started running non-optimized or unoptimized code. So this is also useful, and I can also switch to this textual representation, so to speak, and then I can go down to, where is it? This bottom-up profile view, which gives the same output. So as we see, this getVisitors function is being on the CPU 18% time of its parent. So that's all there is to profiling. There is more, but I don't want to consume too much time in digging into profiling stuff. So, but as you can see, you have a lot of options when you need to profile or debug Node.js. And most of the time, it's not the lack of data. You'll have a bulk load of data, and you'll have to figure out what part of it to cherry pick from, basically. The next topic that we'll discuss is clustering. And the Node.js, as you know, runs on a single thread basically, or single CPU core. And actually, it's not 100% true, because the libUI library in the background can use its own thread pool, and especially that happens when it does a lot of file writing on the system, like a file I/O thing. However, since the main event loop is on a single thread, and most of the time the Node.js is on the main event loop, you can, for all practical reasons, consider Node.js as a single-threaded application, basically. And clustering is a really fun topic, and if you want to dive deep into the topic, you can read the links provided on this footnotes, basically. But what it does in the gist of it is to get a connection and multiplex it to different cores and kind of load balance the connection evenly, as if there is a load balancer in your machine, and as if there are a separate Node.js server on each and single one of your CPU cores. So since we can use clustering module to load balance evenly our Node.js process, the next question might be, how many cores per machine shall I allocate, or how big or how small shall my machine be? And it also again depends on the situation, but the rule of thumb is for optimum scalability or for optimum performance, basically 2 to 4 cores per virtual machine has been ideal most of the time. And since the cost of virtualization is negligible nowadays, you can even ditch the cluster module entirely, and you can go with single processor, lightweight containers, and put a load balancer in front of them, like an Nginx or HA proxy or something like that. So that's also an option that's totally viable. But clustering has a bunch of use cases that makes it promising or appealing. One of them is zero downtime rolling deployments, for instance. And when we cluster our application, it will look like this. We have a clustered module, and we'll have 2 API nodes bound to that clustered instance, and we'll still be connecting them with a message bus. And in the source code, it's not really hard to do the clustering. So we fork our workers, and if our process is master, we fork them, and if the process is not master, we do our actual logic, where the place that we introduce bugs, basically. So this is how cluster module works, and this is a simplified application or simplified example to just show you the concept. The source code in the GitHub repository is a little involved than that, but that's basically the gist of it, and this is basically good enough for most of the cases. And the other useful pattern when you deal with loosely coupled networking applications that communicate over a message bus, as in our demo applications right now, is the circuit breaker pattern. And it's a really useful pattern. You can learn more about it by going down to the links that I have provided below. However, the easy way to see how it works is to jump through the source code, I guess. In this source code, we have this API endpoint that we make a GraphQL request to a certain endpoint. Like, is it working? No. Anyway, it's not working. Anyway, so we do a API request, and that API request might consume some CPU. So to make sure that our server is able to respond to it, we first check if our server is available to allocate adequate amount of CPU for our request, basically. Otherwise, if we are not able to respond to the client, and if our server is busy, and if we still try to do this computationally heavy operation, then it will be an additional burden on the clients that are already connected to the server. So we first check for the circuit's availability, and if the server is not busy, we continue with our operation. And if the server is busy, we return the client with a 503, the server is busy, please come back later. This thing is something that you have been familiar if you are using Netflix as a product, maybe. I'm not, blaming on them. It's really the way it works, basically. And Netflix is one of the pioneers that have introduced this circuit breaker pattern, to clarify my, my phrasing. So that's this thing. So if the process is too busy, then you can just cut it out without doing some extra work. so that you don't have to allocate your precious CPU resources on something that that will fail eventually. And then we wait for a while, and at that time, probably we'll be adding a bunch of additional services to our autoscale group, basically, and then the load on our server will decrease, and then we'll be able to respond to our clients. And this example is kind of a simplified version of the circuit breaker pattern again, just to show you the overall concept of how it works. We have glossed over certain parts of it, like exponential backing of the countdown timer. And this is not also fully implementing the circuit breaker state machine, so to speak. And if you want, you can go to this links below and learn or use or get used to the examples of a more canonical example of this circuit breaker pattern. So that's all there is with the circuit breaker. And the good thing about circuit breaker is you don't have to. You can use it with any kind of metric, or you can use it with a set of combination of those metrics. You can even use it to rate limit your API maybe. But most of the time, this pattern is useful when you have to rely on an external service that may or may not function well, and then you are kind of cutting out the response and directly returning to your clients the unavailability of the service if it's failing. So it's a really useful pattern, and I would suggest you to do a research on it if you haven't done so. So where have we been lately? We had a clustered application. We had a message bus that was loosely coupling them. And we are missing something in this picture. Our API services have inline memory caches on them, as we have seen. And since each of our clustered API services is using its own cached memory, we might have an affinity issue, basically. And since we are using this memory as a cache, it doesn't matter that much. But if you are using this memory as a session store, for instance, then you'll hit into a session stickiness problem. And maintaining or sustaining a sticky session on a highly available, highly distributed, loosely coupled cloud architecture is a problem. And it's also, is there a question over there? Okay. So, and also, it's not recommended to have a stateful API service, but it's live. Sometimes you have to. And if you have to do this, the best practice is to take out your memory into a distributed memory store like Redis and make your API services stateless in that. And if we take out the memory of API and compute cluster to Redis, then we convert them by default to stateless instances again. And being stateless is good because you can swap them out easily. You can scale out and scale down things. And you can also define auto-scale groups if you are monitoring correct metrics, and add more resources dynamically when you need them and remove resources when you don't need them. And if you need some additional API routing power, so to speak, you can front the API services with a load balancer, for instance. And also scaling out this compute service will also be easy. You'll just add another compute virtual box or virtual machine onto your cluster, and just then register those compute service instances to your message bus, and you'll be done. So that's it for auto-scalability. And when we are scaling things out, as we saw in the former slide, we are using a load balancer. So as a load balancer, I highly suggest you to use a load balancer as a service. One reason for that is as a service solution gives you virtually infinite scalability, and also it protects you from things like distributed denial of service attacks. So it's really something that you don't have to deal with yourself. And sometimes you might need to, along with your software as a service load balancer, you might need to use a software load balancer as well, like Nginx or HAProxy. And you can even write your own load balancing code in certain use cases. And if you want to spend, I don't know, $30,000, $40,000 per machine, you can buy hardware load balancer, but I'm at Cisco and I haven't seen people doing it basically. So that was it. And as we said, we can even write load balancer as a service in Node.js with a couple of lines of code. So here we have a mapping of different API nodes basically, and we are doing a round-robin load balancing by using a library called Bouncy. And if you want, you can even do SSL termination in your Node.js code, Node.js load balancing code. But I highly recommend you not to do that because terminating SSL is CPU intensive, and Node doesn't like CPU intensive operations. But you might wonder why we need that kind of a load balancing software in Node.js to begin with in the first place. One reason might be you might need to do some sophisticated filtering or parsing on your request and response headers, and your as a service load balancer or your Nginx or HA proxy or whatever is not capable of doing that. So there are needs for that, and this kind of code works pretty well in and of itself. It's not as fast as a software load balancer, but it's good enough for certain purposes. So we set up our load balancer, and we are load balancing in our cluster to different sets of nodes basically. And what if our API or our API becomes really popular, and we reach the limits of single data center, we are overflowing the network of entire data center. Then in that case, that would be the least of your problems, honestly. But it means that you'll need to set up a DNS and do some round-robin DNS routing for your system. And to do that, you'll first install an identical version of your infrastructure to a different region. And even if there is not that much of a load in your region, there might be other reasons to do this kind of a setup. One reason might be the fact that you want to be geographically close to your certain set of your clients to decrease the latency. And another reason might be for the purpose of being highly available or resilient, so that if there is some catastrophic event in a certain region, you'll still continue to do your service in different regions. And no matter what the reason is, to do this kind of a setup, you'll have to configure your DNS, either using a round-robin DNS service, or you can do some different rules if your provider supports it, like latency-based routing or proximity-based routing. And setting up a round-robin DNS is relatively easy. You just put a bunch of A records for your DNS configuration for each and every single load balancer that you have. And if you are using a load balancer as a service solution, then there might be web interfaces and API bindings to do that for you, so that you can automate this process basically, and it will be much easier. And at this point, I'd like to mention you one fact. Your DNS is the first level of defense, and your load balancers are the second level of defense against a distributed denial of service attack. So you should ask and discuss with your provider what kind of preventative measures they provide against DDoS and other security metrics in that regard, and your DNS and also on your software as a service load balancers. Some providers give really good precautions, and some might be a little lousy on that regard. So it might be really useful to talk to them first before starting that kind of a setup basically. And also, as we are creating our setup in different regions, we need to define replication groups so that our data stores will be also in sync. And this is a non-trivial task to replicate a Redis cluster in different geographical regions. So you might sometimes be better off, if you are at this point, I would say I would just ditch my Redis and start using a memory as a service solution instead of rolling my own Redis instance, because the maintenance is worth the cost basically, and I would not dare to manage my own replication layer. But it depends on your situation, and you can add more and more clusters to autoscale group if you need so, and this will help you scale out virtually infinitely. There will be a bunch of stuff, issues, of course. Your message queue might be congested, and then you'll need to do some other magic to, unfuddle your message queue. But that's a topic of a different talk, maybe. So one question that arises after this scenario is, as the number of components that you have increases and as the number of moving parts in your system increases, then the inevitable problem is, how are you going to manage all this complexity, basically? And that's the task of infrastructure and configuration management tools. And those kind of tools are dime a dozen, basically. There is Salt Cloud. If you are using AWS, there is CloudFormation. You can use Chef, Puppet, Ansible. And if you ask me, all of them are the same thing with different implementations. So I'm not advocating against or for or against using some of these tools. I'll just give you a bunch of tips to make your life easier or help you sleep more at night if you are using a load configuration management service for your needs. And the first thing that you should be aware of is never, ever, forever use hard-coded IPs in your source code, in your configuration files, ever. The reason is, the reason that you use this IP is to locate a resource. And guess what? Locating resources is the job of the DNS server. So instead of reinventing DNS yourself, you should let the DNS do its job and use a DNS alias for that. This will save a lot of your lives, and I have seen a lot of instances of this being not used properly, and people trying to generate configuration files, use hard-coded IP addresses in the source code. This is one tip that I can give you to save the day for you. And the second thing is, keep your configuration in environment variables. This is also a common misuse I sometimes see. If you have borrowed a legacy production application, you might have a config YAML in some folder, a config blah blah JSON in some other folder. There will be a plain old config.ini in some other folder, and it's really a hassle to manage all these config files in different formats, parse them, get data in and out of them, and also even if you find a way to manage them, it's likely that you might inadvertently check in those config files to your source control system and then cause a security leak. So just keep them in an environment variable in a central location, and you'll thank me later afterwards, maybe. So that's it for the configuration management, I guess. So we have created our cluster. We are replicating across regions. We are using latency-based load balancing, for instance. And moreover, we have implemented a CI/CD pipeline, so to speak, let's say. And we are running tests. We have 100% test coverage. Our integration is doing great. So is it just ponies and rainbows right now? Or do we have some problems that we need to figure out as well? So as we can see, there are a bunch of things that I need to highlight on this slide that are problematic right now. What's the common thing about these nodes, you might ask? These are our single points of failures. So if you want to make your application highly available, then you start with making them highly available. Because if any of the nodes that you see kind of goes down or breaks or gets corrupted for some reason, either part of your application will be severely damaged or your service quality will drastically degrade. So making it highly available would be one of your main goals. And for the load balancer, if you are managing your own load balancers for certain cases, you can use this keep lived in Linux operating systems to make an active failover case to make it highly available. And actually, not only load balancers, you can use keep lived for any kind of network resource that you want to make HA. And you can go to this link. It kind of summarizes the routing protocol that the keep lived uses, then gives additional pointers to dive in deeper, basically. And while we are at the point of load balancers, it's a best practice to terminate your SSL connections as early as possible. And terminating SSL at the load balancer layer is the suggested way of doing this. Again, I have seen certain implications. Some certain clients might be stubborn and say that I want end-to-end SSL encryption, so you have to, do the SSL termination in the source code of your Node.js. So if they want, you have to give them. So that's their option, but it will come with a performance cost. But the best practice is to terminate it at the load balancer layer, basically. And if you are using a load balancing as a service, then this will be most of the time will be provided for you. And if you are using a software load balancer, then you can use the start tool to do the termination for yourself. And making your message queue and making your memory data store highly available and redundant is also non-trivial. And this will also cover an entire day maybe of its own. So I won't dive into the depth of it. If you are interested, you can look at the links provided down below in the footnote to get an understanding of how you can cluster and scale out your Redis and RabbitMQ. And as I said, there is always as-a-service solutions for this so that you don't have to do this scaling architecture yourself, and you can, you can do something fun, like making something useful maybe. And the next thing is building redundancy everywhere. So we have built redundancy on certain nodes, but we also need to write redundant code. What I mean by that is maybe we'd like to create a heartbeat checker in our source code, like a checking script that runs in certain intervals. And when something wrong happens with the service, it will notify our orchestration layer so that it can either tear down our service or reboot some instances or update our load balancing configuration and stuff like that. And this kind of thing is actually the duty of our service discovery tool, so to speak. But you might if you are into the DevOps stuff, you'll find yourself writing check scripts all over and over again. So this is something that you cannot avoid. You'll have to ensure your system and your source code is redundant at all times, basically. So Yep. Questions? Okay. So we have gone a long way. We have started with a single monolithic API architecture, and we have seen certain techniques to cluster it and scale it out to make it a highly distributed, resilient, highly scalable software architecture of itself. And I'd like to close this talk by indicating a certain fact. Your scalability needs and your redundancy needs will be totally unique to you. So some of the tips that I have given in this talk might apply to you, but your adventure, your scalability journey might be much different than any others, and it will be totally for you, totally unique and totally tailored for your use case. So I hope that this tutorial will be helpful in guiding you through the hoops of scaling an application, and it will help you scale out your Node.js application architecture, and it will help you in your scalability journey as well. Having said that, I think I have a couple of minutes for questions, so I can have them if you have any. Okay. Mm-hmm.
Like a C program follows Java. Well, how do you feel about building this like Java program, use like the Java modules, like that way you can talk to it like a bridge? It gives you the advantage of being able to basically load it and talk to it like it's a JavaScript object.
Yeah, it's also an option. The reason that I exemplified C and C++ is the fact that they are relatively faster than Java. And the reason I didn't give, say, an assembler program for an example is it's really pain in the rear to write an assembly code, basically. But it's an option, and it depends. It also depends on the skill set of your team, obviously. So if you are a Java house, then you might want to write your performance efficient code in Java instead of writing in C++. But if you are more like a C++ house that does some embedded system programming, then you might prefer to do it in C++ maybe. So it's totally, and honestly, I haven't seen too much of that kind of a requirement, and most of the time, instead of going that route and writing a highly efficient code, you end up adding a bunch of more servers in your array, and it will be much more efficient cost-wise because the development effort that you do to convert this code to C or Java is not does not correspond to the cost of adding an additional box to your cluster, basically. Yep. So, any other questions? Okay. So, thank you very much for your attention. I'll be outside the lobby if you want to discuss in depth about other stuff, and you can talk with me about Node.js, JavaScript, live, anything, and I'll be available. Thank you very much.